Hi everyone, it's Miss Lloyd again. Today we are going to be looking at trigonometric functions for acute angles. Those are the tiny ones because they're just so adorable. It's okay. I know I'm weird. Everyone else can get over it. I'ma be me. So, when we're looking at the definition of sine, cosine, tangent. So, if you've taken geometry, which majority of my kids have, you should remember this thing called SOHCAHTOA. So this is talking about sine, cosine, and tangent and which parts of a right triangle you're looking at when it comes to each of those functions. So if I have some xy value, so I have a line that's going through that. When I say going through, I mean actually going through the point. So there now it's going through the point. So it's creating an angle. We like to create a triangle from this. So I have my angle down here in the corner. Remember, we always start in standard position, so on the positive x-axis. So I'm looking at this little angle here is my theta, whenever we're talking about the sine of theta, cosine theta, tangent of theta, etc. And then I'm going to create a triangle by dropping down from there and looking just at this part, which will end up being our hypotenuse. Oh, that was a terrible line. That one's a bit better. And then we're only focusing on this part here from the origin to where we drop down. So when we look at this, the orange that I made here, this is the opposite side because it's the side that's not touching my theta. So theta is made up of the green and the blue, so this orange is my opposite side. Because it's going straight up and down, this is going to have the same length as the y value. When I look at the blue part, this is going to be my adjacent side because it is touching my theta, but it's not the hypotenuse. And because this is horizontal and it stops at directly below where that point is that I made, this has a length of x, or a value of x, whatever that x is from the point that I had made at the very start. And then my hypotenuse. This is across from my 90-degree angle, so opposite my 90-degree angle that I made whenever I dropped the line down. And typically when we're looking at this, we're going to be using the letter R. This comes in handy. The reason why we use R is for when we start looking at the unit circle. That's not something that we're going to be looking at in this chapter, but the R comes from the radius of the unit circle. So something that we'll circle back to if we end up getting the time for it this year. And so when we're looking at this sine, so that's the SO of the SOHCAHTOA. Whenever I'm looking at sine, we abbreviate sine to just SIN. I'm not talking about sin, I'm talking about sine. It's the opposite side over the hypotenuse. So the opposite side we have said is a value of y. We're going to put that over our hypotenuse, which we've labeled as r. For cosine, we labeled that as cos of theta, and that's the adjacent over the hypotenuse. It's a ka part, ka. And we've labeled our adjacent x, and that's always going to be over our hypotenuse, which again we've labeled as r. R, maybe. I'm okay. It's been a while here in isolation. A very long while. Anyway, tangent we like to abbreviate as tan. So sometimes you see some mathematicians making jokes about tan lines, and that's going to be our opposite over adjacent. So our y over our x value. And so these are the parts of that triangle that we're talking about, the lengths that we're talking about whenever we're asking for the sine, cosine, tangent of whatever that angle theta is. And so here is basically the same thing but in words. So the opposite side over the hypotenuse in order to get your sine of whatever the angle is. Cosine of whatever the angle is equal to the adjacent side over the hypotenuse. And tangent of whatever that angle theta is equal to opposite over the adjacent side. So when it comes to reciprocal, so reciprocal you should have heard of before when it comes to fractions. It means we're flipping the fraction. So whenever we're looking at the reciprocal of cosecant, so we change cosecant to CSC. That's how we shorten cosecant. This is the reciprocal of sine. So it's the same as 1 over my sine of theta. And if sine is equal to, we set up here, opposite over hypotenuse, that means I'm flipping that and it becomes the hypotenuse over the opposite. And I'll go ahead and put those labels in. So that's Y and R. When it comes to secant, we label this as SEC. Hold on a sec. That's secant, and this is 1 over our cosine, this reciprocal of cosine. So we flipped our cosine fraction, which means we now have the hypotenuse over our adjacent side, which is the x value again. And then cotangent, this one I think is the easiest to remember because it is the reciprocal of tangent. So we shorten this to cot, C-O-T, that's our cotangent. So it's 1 over our tangent. So we flip our tangent. We said before that that was opposite over adjacent. So then this becomes adjacent over opposite. And so those are ones to remember. These are also on the formula sheet for my students when it comes to this chapter. This is something that, in case you don't necessarily have it memorized, it is on the formula sheet for you. Whenever you get to pre-calc though, you're out of luck. It ain't gonna be on there. And then we have some co-function relations. So if we wanted to relate something and add that is sine into cosine, or if it's cosine and relating it into sine, and we actually know what theta is, we can rearrange it using these formulas. And these are also on the formula sheet for my students. These I definitely would not expect them to memorize. We don't use them very often in my class. Next, we're looking at some special right triangles. So this first one is a 30, 60, 90 triangle. So the great thing about the relationship between the 30 and the 60 and the 90, these are all multiples of 3. So they relate to each other in various ways. They're all multiples of 30. So across from 30, that's our shortest side. That's going to be 1. Across from 60 degrees is going to be square root 3. And across from our 90 degrees, which is our hypotenuse, is going to be 2. So this happens every single time you have a 30, 60, 90 triangle. They reduce down to this very basic ratio of 1, square root 3, and 2. So we can always dial back to this whenever we have a 30, 60, 90 triangle, every single time, no matter what. And then for a 45, 45, 90 triangle, because we have two angles that are the same, that means the sides opposite those angles are going to be the same. So everything kind of reduces down to 1, 1, and then whenever you do the Pythagorean theorem, 1 squared plus 1 squared is equal to 2. So then your hypotenuse is the square root of 2. And again, if you have any kind of 45, 45, 90 triangle, all of the sides boil down to this ratio. So one of our first examples that we're actually going to go through, when an acute angle is in standard position. So standard position means that we're starting on the x-axis like we had before in the last section, if you saw that, my 12.1 section. Its terminal side passes through 2, 4, and they want us to find the sine, cosine, and tangent of whatever that angle is. So first thing I'm going to do is find where 2, 4 is. So I go over 2 and up 4. So I'm going to say it's about here. It's not necessary that it has to be perfect. It's just convenient. So 2, 4. You don't really necessarily need a visual. I'm just a very visual person. I think it makes more sense if we have a visual. So I like to make them every time. And so here is my angle theta. And again, I'm going to drop down a vertical line here, to create my right triangle. So I have my right angle here. This will be my opposite side. And that's going to take my y value, so 4. My adjacent side down here is going to take the x value, which is 2. And then I need to figure out what my hypotenuse is. So this line here that's across from my 90 degrees. Oh gosh, why does that line suck so much? It's I still don't like it. Oh, well, this is kind of what I'm going to just deal with, yeah. So this is my r, and so I have to figure out what that is. So I'm going to use my Pythagorean theorem. So I've got one side squared plus my other side squared equal to my hypotenuses square. I'm going to use green there. So the r squared, we're labeling it r in this case, again, because of the unit circle. So now I've got 16 plus 4 equals my r squared, and so that's going to be 20 is my r squared when I take the square root. Anytime we take a square root like this, we're undoing the square, we would have a plus and minus. Because we're talking about a measurement in this case, we're not going to have the plus minus, we're just going to be using the positives. So our hypotenuse there is always going to be positive in this case. And then when I take the square root of 20, I can reduce that to 2 square root 5. So 2 square root 5 is my hypotenuse. And now I can figure out my sine, cosine, and tangent. And I'm going to use the SOHCAHTOA. SOHCAHTOA. So my sine of whatever this theta is, I know I'm using the opposite. In this case, that was 4. And I'm putting that over my hypotenuse, which was 2 square root 5. I'm going to reduce this a little bit, so I have now 2 over square root 5. And we don't like to have the square root 5 on the bottom. That's not rational. We want to be rational people. So I'm going to multiply both top and bottom by that square root 5 in order to have a rationalized denominator. So we end up with 2 square root 5 over square root 5 times square root 5 just gives us 5. So I've got my sine. Now I'm looking for my cosine. And that's going to be my adjacent over my hypotenuse. So my 2 over my 2 square root 5. So again, here I can reduce, so 1 over square root 5. And again, I need to rationalize that denominator, so I'm going to do the same thing that I did to the sine. I'm just going to duplicate that, move it over. And I end up with square root 5 over 5 for my cosine. And then the last one is my tangent. So I'm doing my opposite over adjacent. Our opposite we said before in sine was 4. And our adjacent is 2, so this one's the nicest one because that just simplifies down to 2. And then we're done. We have our sine, our cosine, and our tangent of whatever the angle theta is. Ta-da! I'm doing spirit fingers, but you can't see it. Such a shame for you. All right, next bit. So find the 6 trigonometric functions, so that means sine, cosine, tangent, and their reciprocals, so the secant, cosecant, and cotangent, we're finding all 6 of those, of an angle theta in standard position, whose terminal side passes through 3, 4. So I kind of already drew just a triangle for this, because I already know that I'm going to need a triangle, so my theta would be here. Again, if we're in standard position, then this bottom side here is going to be the same as my positive x. I just didn't want to draw so many lines, so I kind of drew it this way. And if the point up here is at 3, 4, definitely kind of drew the wrong triangle because that doesn't, it looks like the side that's going to be 3 is longer than the side that's supposed to be 4. But you guys will forgive me, right? And then that means I need to figure out my, y. There we go. I need to figure out what my hypotenuse is, my r. And so that means I need to do my Pythagorean theorem again. Or if you remember, this is actually one of the special Pythagorean triples. So 3, 4, your hypotenuse here is going to be 5. Or you can do the 16 plus the 9 would give you 25, and the square root of 25 would give you 5. And then I'll make that orange. There's a little right angle. So now I need to find all of the functions. So sine of our theta, again, is opposite over hypotenuse. So we're looking at 4 over 5. Cosine, we're looking at adjacent. So 3 over hypotenuse, which is still 5. And then tangent, we're looking at opposite over adjacent, so 4 over 3. And so in order to find the reciprocals, all we're going to do is flip those fractions. So the reciprocal of sine is called cosecant, so the CSC. So that one, instead of being opposite over hypotenuse, it's hypotenuse over opposite, or just a 5 over 4. They're just flipping each of those fractions. And then the reciprocal of cosine is the secant, so the SEC. And that will end up being 5 over 3, our opposite. And then the last one is our cotangent. The reciprocal of tangent, which means we're just flipping what we had for tangent, so 3 over 4. A few different ways to look at it. And now we've got, count them, 1, 2, 3, 4, 5, 6. All 6 of those trig functions. And we're ready for the next bit. And so I have several Greek colleagues, and I know they're going to be so mad at me because I can't remember what this Greek symbol is. So I call it the lollipop because it looks like a lollipop. And I know that's not what it's called because that's not a Greek word, lollipop. So I'm very, very sorry. I know Mr. Kostas tends to check these out, and I apologize profusely for not remembering how to say what that is. But I'm going to call it lollipop. It's basically, we have in English letters, the sine, cosine, and the tangent. And so in order to kind of keep those separate, this is why we start using the Greek alphabet, so that we don't get the variable confused with the trig function. So we tend to use these Greek letters a bit more. Also, Greek is where majority of our math comes from. Greek and in the Middle East as well. We have a lot of our math comes from there. So we gotta know where our roots are. So here what they've given us is the sine of our angle is 5 over 13, which means they've given us our opposite and our hypotenuse. So if I have, again, I'm really sorry, my lollipop thing here, and I draw it very poorly. Maybe I should try it that way. Nope, it kind of looks like a 4 there. So there's our angle with its Greek variable, and I have my right angle here. So I know that this is going to be a right triangle because we are talking about sine, cosine, and tangent, and that's the only time we use these at this point in time is when we have our right triangles. So the opposite of that angle, I'm going to have my 5, and I know across from my 90 degrees, my hypotenuse, I'm going to have 13. So now I need to figure out what my adjacent side is. So I'm going to be using the Pythagorean theorem. And Pythagoras was Greek. He was also afraid of beans, believe it or not. It's very interesting. So 5 squared is equal to, plus, I'm going to label that A for adjacent. So our A squared. And then whenever we solve this out, our A ends up being 12. Another one of the Pythagorean triples. So now I have my adjacent side, I have my hypotenuse, I have my opposite. I'm going to put OP so it doesn't look like it's equal to 0. And so now in order to find cosine, I need my opposite over adjacent. So cosine of, again, I suck at that, my lollipop thing, I'm so sorry, is equal to my adjacent, so 12, over the hypotenuse, which they told us to begin with was 13. And then tangent of my lollipop, oh, I have so many issues, I'm sorry, is equal to my opposite over adjacent, so the 5 that they told me, and the 12 that I found. And that's it. Ta-da! Not too crazy. And then our next one. They've given us the triangle already. They've drawn it all out. That's really nice. The length of one side of the triangle is given, and they want us to find the lengths of the other 2 sides. So typically when we have a right triangle, they give us 2 sides, and we find one side. This one's a little bit different. But then it's actually not too crazy because one thing that they've given us is that this is a 45, 45, 90 triangle. So this should have a little degree symbol so we know that it's degrees and not radians. And then I have my 90 degree here. And we know when it comes to a 45, 45, 90 triangle, because our degrees here, our angles here are the same, that means that these sides here will be the same. So our sides, a squared, and in this case c squared, those are going to be equal to the hypotenuse squared. So in this case, they gave us 12 for our hypotenuse across from our 90 degrees. And since here A and C are supposed to be the same, since it's a 45, 45, 90 triangle, I'm going to replace my c squared with an a squared. So then I just have one variable that I'm looking for instead of two. And so now I've got my a squared plus a squared, which is going to give me 2a squared is equal to, I already wrote down this, 12 squared is 144. Dividing that over, I'm going to end up with 72. So dividing my 2 over, a squared is going to be equal to 72. And then taking the square root of 72, again, we're looking at measurements here, so we're going to keep everything positive, not do the plus minus. So a is going to be equal to, I can reduce it a bit, take out a 36, so 6 square root 2. And since a is 6 square root 2, and a and c are equal, then I know that side c is also 6 square root 2. And we're done! Ta-da! Not crazy. Well, I am. Math isn't. I think that's the only reason I'm okay. Alright, so using the diagram to find the measure of angle x. So we're trying to figure out what this angle here is. So they've told us one side is 0.25, the other side is 0.5. I notice a relationship between 0.25 and 5. 0.5 is 2 times the 0.25. So it's likely that since we have that kind of relationship, so this is 1, that's 2. This is likely going to be one of our special triangles, because one of our special triangles has that same kind of relationship with its shortest side and its hypotenuse. And whenever we go back to look at it, that's a 30, 60, 90 triangle. And so our 30, 60, 90 triangle, whenever we're looking at this, is we want to figure out what x is, and that's across from our shortest side. So that means it's going to be our smallest angle. So if this is a 30, 60, 90 triangle, then that means that our angle of x is going to be equal to 30 degrees. And that's it. Ta-da! Not too crazy. So if you are one of my students, your homework assignment is on the LMS page. Again, it's not all of those, but there's going to be a few of those in there. If you are my student or not, please like, share, and subscribe. And be sure, especially, to share this with anyone who might need it, especially in the time that we're in right now. If they want to hear the ramblings of a crazy math teacher, it might be a little entertaining. They might say, you know what? I'm not as bad off as she is. Spread the love.